In the first example, we are going to solve through finite element analysis a problem that we were actually able to solve previously using the continuous method, because in this problem we will have a constant cross-section, constant material, which means our density is constant and our Young's modulus is constant. So we did already solve this before, so we already know what the natural frequencies of this should be in their exact values. Now with FEA we can compare what we're going to get with this method to what we know to be the true values. So we're told specifically for this example to use a 4-element FEA, and I'm going to use a constant sized mesh. So I'm going to take this beam, and originally it's this continuous beam, and I'm going to split it into 4 equally sized elements here. So we're told to use L equals 1 meter. For the moment though, I'll keep everything algebraic and say that each one of these elements is going to have a length of L over 4, since I have 4 elements here. And each element is going to have a node on either side, and ultimately the node is what we are trying to track. So what we're saying is, instead of finding the displacement at all points along the beam, we're only going to be able to find it along these nodes, which I'm going to number as 1, 2, 3, 4, and 5. And what I'm tracking will be U1, U2, U3, U4, and U5. So ultimately these are what we're going to be solving for, is U of t for only these 5 points. So at the wall, a quarter of the way through, half, 3/4, and all the way at L, we'll be tracking those displacements. And I'm going to name my elements here, also left to right, as 1, 2, 3, and 4. So we see each element on the left has a node attached, and on the right has a node attached. And neighboring elements are going to share a node. So ultimately what we're going to get to is, this is the vector of degrees of freedom we are going to solve for. 1, 2, 3, 4. So 5 degrees of freedom we are going to have in this one. And where we're going is we're going to get some mass matrix M that we're going to multiply by this, plus some stiffness matrix K that we're going to multiply. And this is a free vibrating system, an autonomous system, so the right-hand side will be 0. So this M and this K that we're going to get are the global mass and the global stiffness matrices. But we see that this equation of motion here is just going to look like a multi-degree of freedom system that we've analyzed already in Unit 2. So the first step is going to be creating this M and this K. And we already know, because this U is going to be a column vector, that M is going to be 5 by 5, because U double prime is a 5 by 1 matrix. K is then also going to be 5 by 5, because it's being multiplied by this 5 by 1, equals then a 5 by 1 of zeros. So we'll start there, and then we'll apply boundary conditions. We'll be interested in finding the natural frequencies. And again, we've already looked at this one analytically, so we know what some of these results should be. But let's see what we are trying to find here before we start putting things together in MATLAB. So we want to study the resulting vibrations, so we want to find U of t, which we're going to get through a principal coordinate analysis. And also in this one, let's look at the natural frequencies we have, since we know what they are supposed to be. And before we get into the MATLAB though, the local mass matrix, because this is an axial problem, we know that we want to use here that for each element, we can calculate it by rho AL over 6 times this 2, 1, 1, 2 matrix. And the local stiffness matrix is going to be calculated with this AE over L, 1, -1, -1, 1. And keep in mind here that this L that we use is going to be the length of the element. It's not the length of the entire beam in this case. So L, little l in these equations, is really the L over 4, which will be 0.25. And also, it won't really come up in this one, but if we look at the local matrices we're using, we have this rho, this A, and this E. That also is going to be local to each element that we are talking about. So it would be, let's say we're talking about the first element, its density, its cross-sectional area, its Young's modulus. In this example, though, every element has the same rho, A, and E, so we're not going to have to worry about changing that, but in general, that doesn't have to be true, and that's going to be the benefit of using finite element analysis, is we're going to be able to solve the motion of systems that don't have constant rho, E, and A. When we are assembling our global matrix for mass and stiffness, we're going to use what's called a mapping. So if you see how I've labeled my elements and how I have labeled my nodes here, I am going to, in MATLAB, automate this process because eventually I'm going to want to look at systems with more elements and more nodes to it. So I want a consistent way to be able to do this. So I'm just going to make a table here that's going to aid me in this process where I'll have the element name and then the left node and the right node. And it's going to be pretty simple in this case. And we can see what the pattern is going to look like. For each element, let's see, in element 1, its left node is 1, its right node is 2. For element 2, left is 2, 3, 3, 4, and 4, and 5 for element 4. So straightforward in this one. It can get more complicated when we get to 2 dimensions and higher. And when we get to transverse beams, we want to pay attention because we'll have multiple nodes per edge, but that will wait for 2 sections from now. But you'll see that I'm doing this, and then this is going to continue in the case where I have more elements, that same pattern of what's the left node, what's the right node is going to come with it. Bringing into MATLAB, I'm going to start setting the stage for creating first these global matrices. So this is hard-coded in here. It will only work with 5 nodes, 4 elements, and we'll see that we'll expand upon that soon. All right, so capital N I am using as my number of nodes in my version of the code, and my number of elements will always be 1 fewer than the number of nodes when I'm dealing with these 1D axial problems. So N is 5, and the number of elements is going to be 4. But I am setting this up for future use as well. So the global stiffness and mass matrices are going to start as 5x5 systems because I have originally 5 degrees of freedom that I'm using. So I am just pre-allocating them to be 0 matrices. When I go through the assembly process using the local stiffness matrices, we're going to see that this is going to fill in. And I'm going to make this map list vector. So we see here, if I type out what map list is, each row is just what's the left node and the right node for the elements as I go from row 1, 2, 3, and 4, corresponding to elements 1, 2, 3, and 4. And we'll see how that works when I am going through my assembly technique. And finally, the parameters of the system. Every element has the same cross-sectional area. The total length I'm calling capital L, and that's just 1. And then the elemental length is going to be lowercase l, and that's what I use when I am finding the local mass and local stiffness matrices. The Young's modulus, again, constant for all of them, and rho, the density constant for all of them. So I put that in. All right, so now I am going to, in a loop, go element by element. I'm going to calculate that element's local stiffness and mass matrix, and while I'm in the loop, I'm going to superimpose it into the correct location in the global stiffness and mass matrices. So we see what's going on here. 24, 25, I'm making its local 2x2 matrix. And I'll go from 1 to my number of elements. So let's just see what happens for the first element to start. So J is 1, just so I can see some results here. So if I run this, that is element 1's local stiffness matrix. And actually for this problem, each element will have exactly the same local stiffness and mass matrix, but we'll see that changes in subsequent problems. Then I calculate element 1's local mass matrix with these values attached to it. And then these next steps are going to be putting the local matrix into the corresponding place in the global matrix. So this is where that map list is coming into play. So let's see, I'm working on the first row of map list. So that's what's going on here with this map list of J1. So it's looking at the first row only because I'm on the first element right now. So what this is doing first is it's looking where to put the upper left component of this KE. So if we see KE1, that corresponds to the upper left of this 2x2 KE matrix. So we're talking about this first. So it should go into spot 1, 1 of my global matrix because this is talking about node 1. Because this is from element 1, its left element. So that's what I'm seeking here is it's K of what's going to turn out to be 1, 1. So map list here is 1, and map list here is 1 as well. So what I'm doing is I'm taking the current value of it, I'm adding the corresponding location from my local matrix, and then overwriting the value that should go into K at that spot. And what this is going to allow me to do then is superimpose where there's going to be overlaps, which we're going to see is going to happen on node 2 and 3 and 4, where we're overlapping two elements are going to contribute their local stiffness and their local mass to that. So I go through all of the locations in the global K, capital K, and then I'm putting in the upper left, the upper right, the lower left, and the lower right of my local stiffness matrix. And then I'm going to do the exact same thing for the mass matrix. I'm going to populate where should the upper left, upper right, lower left, lower right go from the local matrix into that global matrix. So let me just see what happens here for j equals 1. And we can see how this progresses. So I'll run, not in the for loop yet, but just this material. And now let's look at k. So what it did is it slotted into the correct spot my local matrix into row 1 and row 2, column 1 and column 2, because this is pertaining to node 1 and node 2. So let's go on to, I'll make j equal to 2 and see what happens when I'm now talking about element 2. So element 2 is attached on the left to node 2 and on the right to node 3. So now with j equal to 2, I'll just run the inside of this. And it populated it, and let's look at k. So now we see this value changed from the previous time because I have the lower right from my element 1 and the upper left from my element 2 being added together. And then put in the rest of the values in the correct place. And if we look at m, the same idea there. This element 2 is having contributions from the lower right of element 1 and the upper left of element 2. And it hasn't gotten to the other ones yet. So let me just rerun this so I can get my m and my k global matrices all assembled here. Okay, so it's all run. So now we see the k going through all 4 of the elements and the m going through all 4 of the elements. And now the global m and the global k have been assembled. Global matrices are now assembled. We have our m, we have our k. So the next step is going to be in the code enforcing the boundary conditions that we need to enforce. So going back up here, if we remember from the analytic problem or thinking about it now, we had 2 boundary conditions. We had the displacement at the wall was 0, and the strain, the axial strain at L was 0 as well. So I'll write those down. So u of 0 should be 0, and u prime of L is also 0. When we went through this with the continuous, treating as a continuous beam with the PDE method, we had to enforce both of those. As far as the finite element code goes, the strain boundary condition, we don't need to change anything in our code or modify anything to accommodate that. So it is still a boundary condition. We just don't have to do anything special for the strain. However, for u of 0 equals 0, we do. So u of 0 is the wall in our finite element model. That is u1. So u of 0 is u1. Now, because it's a position boundary condition, we do need to modify our system. Because what's going to happen is we now know in U that U of 1 is always 0. So it's not an unknown. We still don't know U2, 3, 4, 5 at all points in time, but we do know that U1 is 0 at all points in time. So what are we going to do? In order to enforce that, let's go back to what is going on here. I'll just do it for the M, but for the K, it's going to be the same idea. I have U1, 2, 3, 4, and 5. So by setting, so this is my M matrix, but K will be the same idea. And actually this would use the double dots. We also know the acceleration is going to be 0 as well. So basically I need to eliminate that the row and first column of M, and that will guarantee that U1 and U1 double dot are going to always be 0. And it's going to be the same thing for K. I want to eliminate its first row and its first column. But specifically, it's not always the first row in the first column. It's because U1 is the one that is always set to 0. So it's really the index of whatever U value or whatever degree of freedom is going to be permanently set to 0. So really what we're going to have then is a smaller system, because now we're analyzing only 4 degrees of freedom, U2 through 5, since we already know U1, with a modified M. I'll call it, I guess, M tilde for the moment. Just that is reflecting that it's M, but with the first row and the first column removed. And that's what I'll call M tilde. So really what we're doing is we're only having to solve for these 4 degrees of freedom going forward. And that's how we enforce the boundary conditions in the finite element code when we have homogeneous boundary conditions like we have here. So let's see how we can do that in the code. So in the code, it's pretty straightforward. So I still have my M and my K hanging out here. So notice they are right now 5 by 5s. So for the boundary conditions, because U1 is always going to be 0, I want to remove the first row and column of K and M. So what I'm doing in 38 and 39 is I'm taking K, I'm taking the second row through the last row, and the second column through the last column, and overwriting K with that value. So this is what on the paper I was just calling M tilde or K tilde. It's just that reduced M. I don't need the original anymore, so I'm just going to overwrite it. So if I run these lines, let's look at our M now. So notice it's 4 by 4, and K is 4 by 4. That first row, first column have been removed, and I'm left with just the second through last row and column. With the reduced M and K, now I can treat it just like the multi-degree of freedom systems I did in Unit 2. Boundary conditions have been enforced, so now I'm ready for really the same procedure that I've already done before. I want to find the eigensystem of M inverse times K, which I can do copying virtually the same thing we've seen before. So for here, I get, it's now a 4 degree of freedom system, so I am going to get 4 mode shapes, and I'm going to get 4 natural frequencies. And if we see here, taking the square root of my eigenvalues, these are the 4 natural frequencies. They're not sorted yet. I'll do that in a second. Now I can only see 4 natural frequencies because I had, well, originally 5 degrees of freedom. One of them was set to 0. That reduced my degrees of freedom really to 4. And I have as many natural frequencies as I have degrees of freedom. Now, this is a problem where we already solved it analytically. We know what the natural frequencies should be. So I have just copied from the previous time we solved this what that equation was. And that was this 2n minus 1 times pi times c over 2l. And I'm just going to put in n is 1 to 4 because I only want the first 4 natural frequencies. So let's see what those were, or remember what those were from when we previously solved this. And if I display them, all right, so here they are in order. This is from the analytic solution. So the lowest was 7980 about. This is in radians per second, and the highest 66,000 radians per second. Now let's see what we get from the FEA. Right? The lowest natural frequency from the FEA, we get 7928 compared to 7980 or so. So that's not too bad. Then we get 23,000, let's call it 23,800 versus the correct value, which we do already know is 25,000. Then the third is 39 versus about 46. And then we have 55.5 versus 66. So we see what's happening here is the first natural frequencies from our FEA versus the actual are fairly close. But then as we go up in frequency, that percent difference between what we know is the value and what we're getting from the FEA starts to get larger and larger. And that is going to tend to happen as we get those larger frequencies. The larger we get, the more initially at least deviation there is from the true answer. Again, we have the benefit in this problem that we've already were able to solve this analytically, but in general for more complicated problems, we probably won't have an analytic solution to compare it to. And we'll get to that when we talk about convergence in a couple of videos. But here we see that at least for the first two natural frequencies, we're not too far off what the true answer should be. Now let's go on and solve for the behavior of our degrees of freedom using principal coordinate analysis. And this is no different than when we saw it the first time when we were looking at the multi-degree of freedom systems. So first, I'm going to need to find out what my initial conditions are. So same initial conditions as I had when I solved this analytically. I'm going to use this force, and I'm going to use that to find the displacement of, in this case, just those 5 nodes. Although again, U1 is gone at this point. I know it's 0. So everything from after I eliminated in 38 and 39, I am only applying things to U2, 3, 4, and 5. Now later on, I can put U1 back in because I know that it's 0. But notice I only have 4 nodes left after line 39, at least in my version of this code. So using principal coordinates, I can take this modal matrix V, and I still want to find the mass normalized modal matrix, which I do first. And I find then this xn, I'm calling it in this code. So xn is my mass normalized modal matrix. Then I can apply my initial conditions. In this case, I can do this K inverse times P, and I have to define it first. So P was that forcing. I'm only applying the applied load on the end there. So U0, those are my initial conditions on U2, 3, 4, and 5. And then my initial velocities, well, they're all 0 because we are starting at rest. So that is also 0 velocity on U2 dot, U3 dot, U4 dot, and U5 dot. I can convert from my original coordinate system into my principal coordinate system. Then I can solve for the principal coordinates like I have before, and then convert everything back into the original coordinates. So to refresh this, you can go back to the multi-degree of freedom and see how we solved those. But I'm using these 4 natural frequencies to find my 4 Q values, then going from my Q values back into my solutions for U2, 3, 4, and 5. So I'll just plot the results from this segment. So this is what I get for the behavior of these U2, 3, 4, and 5. Now U5 is this purple line. That is going to be the displacement at the end of it. U4 is going to be 3/4 of the way through, U3 is going to be half the way through, and U2 is going to be 1/4 of the way through because I'm using these 4 elements. And then U1 is not pictured, it's always 0 because it's at the wall. So we see we do get these oscillations here that are roughly look like triangles, but they're a lot wavier here. So keep in mind before we compare this to when we solve this analytically, that right now our solutions are based only on 4 natural frequencies, and we already know that the 4 natural frequencies that we found all have error in them, a good amount of error compared to what we know they should be. So the natural frequencies are certainly incorrect, and there's only 4 of them. When we plotted this with the analytic version, which I'll compare it to in a minute, we used many more natural frequencies when we were doing that summation to get that result. So going back to what we saw in the previous section for the axial bar, let me rerun and then we can compare it more one-to-one here. And let's look at its displacements for those same points. All right, so running this, now this is where we have these very sharp oscillations, at least for, this is our U5 now, is what I'm calling U sub L or U at L in this system. So we have these very sharp peaks. And for the halfway point, for the quarter wave point, we had that flat dwell, and then it went straight down to another dwell, straight up to another dwell, and then we had those nice linear changeovers. And the same thing was true for the halfway point and the quarter wave point. So let's compare these more side to side though. All right, so I'm comparing just those output graphs now so we can get a nice qualitative assessment. We can do a more quantitative assessment later because this is just a demonstration of choosing an arbitrary number of elements and seeing how our system behaves. So if we look on the left, that's from the FEA we just did with only those 4 elements, 5 nodes, and the right is from the analytic solution from the previous section. So notice at least the values, the amplitudes are not that far off. For the end, we're getting, again, it goes a little bit over 2 micrometers, and we get about 2.5 over here for the analytic solution, which again, we know is the correct solution. So not bad agreement there. And similarly, if we look at the other places, the halfway point and the quarter wave point, the blue here is the quarter wave point, not too far off from what we see from the analytic, and kind of this reddish is the halfway point, not too far off. So it's not outrageously bad, but we see definitely a lot more waves, a lot more oscillations that shouldn't be there because we're using so few, relatively so few of the natural frequencies to assemble our full solution, and the natural frequencies we do have are not going to be that correct yet. And the same idea with the mode shapes. The mode shapes are not quite correct because we have too few elements at this time. So we're going to revisit this with more detail by using more elements, which is going to give us more natural frequencies. And we're going to see that by using more elements, we get not only more natural frequencies, but the correctness or the accuracy of the natural frequencies as we go from low to high is going to increase with the increase in the number of elements that we are using.